Okay, I see the recording is on now. Let's start today's class. We'll start discussing about various network topologies today. We will see, how different networks will be connected in different types of environments. Okay. Um, okay. I hope you guys can able to see my whiteboard. I'm going to start with a home network. So in a typical home network, what we discussed about how does a typical home connects from our previous class as well. So I'm going to repeat the same on that. So we will be having a laptop, or let's just in case assume we have a laptop, and the laptop will be connected to a what? Wi-Fi router. And the Wi-Fi network will be connected to any service provider that you pay the Wi-Fi bill. Like end of your house or end of your street, they will install a router of their company. All of your routers in your street will be connected to that service provider router. And that service provider router will be connected to their mainstream router inside their data center or their office space, the centralized location. Let's call it as service provider office router. And that will be connected to the internet. So in this case, when we are trying to go to google.com, on the internet, so the packet from the packet from the home router comes to Wi-Fi router. When you connect to your SSID, when you make a connection on your router, you will be getting three things, right? So one is IP address, second one is gateway, third one is network size address or subnet mask or subnet, you can call it subnetwork address. Subnet mask. We'll discuss about subnet when we discuss about IP addressing, how we are separating networks, how we are dividing the big network into small networks. We will discuss all of them in our subnetwork mask in that class. But for now, think about like if you have a big network and you wanted to separate them into two different networks, network A, network B, you will use the subnetwork mask. The subnetwork mask is to divide networks is what you need to understand. So in this home network, like we discussed yesterday, the packet has to come from the laptop PC. When you connect your SSID, let's say you sent your packet to your Wi-Fi router using your default gateway, because you will check, your laptop will check the ARP table, right? And the ARP table will not have the MAC address of the google.com, right? It does not have any response of the google.com. So then what the laptop will do, it will check its ARP table. Does it have the MAC address resolution of google.com or not? If it is not there, it will send the packet to the default gateway, which is your Wi-Fi router in this case. And that will be looking into the default routing table and will be sending to the service provider router, because that's the only path. So this is your traditional home network, right? So from here it goes to the office location or go to the internet directly and reach the google.com, and you get the response back directly to your laptop. So this is how a small home network looks like. So, but from a security standpoint, this network is not that secure, because you don't have the security of your Wi-Fi router. If anyone comes from the internet, they can directly, hit you with a lot of traffic, and they can hit your Wi-Fi router pretty bad. So what we can do in that case is we can put a firewall at the edge of your network, right? For example, in the same diagram, I can turn on a firewall here. Okay, I can put a firewall there, and I was able to protect my network. So from your PC, it goes to Wi-Fi router, and it goes to firewall, and then go to your router, and you will go to the service provider router, and then it will go to the internet. So in this case, there can be enabled a security, meaning when I turned on the firewall, I can allow or deny the traffic. So by turning on the firewall, it's act as a security measure here. I can allow or deny traffic here. So using this firewall, I can control what is going outside of my network and what is coming inside my network. I can control that using this firewall. I can do that. But the problem here is when someone inside the home is trying to hit the network, if I have 3 systems inside the same network, and if this is a malicious user, if that malicious user, is trying to attack this computer, then we had an issue, because the firewall sitting outside and this Wi-Fi router is not protecting between the system to system, right? There is a problem inside our home network itself, right? So then there is an issue. That's why what they will do is, if you have a PC and PC, let's say you have 3 PCs in the network. They all connected to the router. So on the same router, they included the firewall functionality. So you can enable the firewall inside the router itself. So that way, if this user want to communicate with this user, or this user want to communicate with this user, we can control it on the router itself by adding the firewall functionality like ACL. ACL is called access control list. Okay. But this cannot do, for example, it cannot control at the application level. What does that mean, right? Let's talk about that in a second now. For example, there is a user. He's trying to go to a website. Okay. The website name is maybe outlook.com. Okay. And Outlook is used for the mails, right? If you want to open your mail, you want to check what you got, you'll use Outlook for, okay? And there is another user. Using the same router, he's trying to do gambling, right? He wants to play cards, right? He wants to go to gambling.com. But we don't want that. We as a network engineer or network administrator, we want to block that, right? So tell me how I can block on the router gambling.com and how I can allow outlook.com. How I can achieve this, guys?
We can provide the IP address to the firewall and ask the firewall to, if any request come to access this IP address, just deny it. And if this IP address come for outlook.com, then you can allow this. Maybe like this we can do.
Yeah, so using the IP address, we can put a rule on the firewall or the ACL. If it is matching this IP, block it. If it is matching this IP, allow it. Okay, that is good. But what if I wanted to allow, for example, now facebook.com, facebook.com, under there is a chat option. Okay. So now the user is trying to go to facebook.com and he is trying to do Facebook chat inside it. I wanted to block the chat option, the facebook.com, but I wanted to allow facebook.com. How I can achieve this on the router, guys? So both facebook.com and facebook.com inside the chat are using the same IP address, but I wanted to block chat. I want to allow facebook.com. How I can achieve this? Any idea? Yeah, this is not possible with the IP addresses because they both are using the same IP addresses. This is not possible. That's why this use case cannot be done using the router. We need an application-aware firewall. So in that case, the firewall can look at the payload. It can look into the header content of the actual data, and it can identify whether the user is using the facebook.com or it's using the application sub-application chat inside the facebook.com. So the firewall can do that. That's why we need firewalls. We cannot do all the functions just with the router itself. So we need application-aware firewalls to do this kind of blocking. Okay, so that's why we put the firewall at the edge. Okay, that's why we put the firewall at the edge. And we control inside traffic using the ACLs inside the same network using the IP addresses. Is this clear till now?
Yes.
Yes.
Okay. Okay, now we understood the home network. Now let's connect a building with 2 floors. Let's see how they will be connected and how they can communicate. Okay, so now we have a building And we as a network engineer, we wanted to make sure we connect that building network to the internet. Okay, let's see that. Building. Office building with the 2 floors. So there is an office building, and let's say there are there are 2 users in the floor 1, and there are 2 users in the floor 2. Okay. So floor 1 devices, they will be connected to switch 1. Floor 2 devices, they will be connected to switch 2. Okay. And switch 1 devices will be switch 1 will be connected to the router. Switch 2 will be connected to the router, and from the router, they will be connected to service provider, and from the service provider, they go to the internet. Okay. So in this case, there are 2 switches, switch 1 and switch 2. And from here, it's the same. The connectivity from here is same, right? So if the floor 1 user wants to talk to user 2 in the floor 1. So what happens? We will put them, both of them in the, all 4 in the same local LAN network, right? Okay. So for example, because they're all part of one LAN, you can use IP addresses 10.0.0.1, to okay. So there are 2 floors here. They want to communicate, right? So 10.0.0.1 will send the broadcast message. Switch 1 will send the packet to all the devices because it's a broadcast message. It will go to the packet will go to router 1, and also it will go to the switch 1 because it's a broadcast message. And switch 1 will get a response saying that, hey, I am 10.0.0.2. So switch 1 will store that in the MAC address table. Switch 1 knows the MAC address of laptop 2 on port 2, and switch 1 will know the MAC address of laptop 1 on port 1. It will store both of them in the CAM table, and they make it communicate between them. We know this all story from yesterday. But if it's want to communicate with floor 2 machine 3 or PC 3, so now the same thing, it will broadcast. Switch 1 will be broadcasting that to the router. Router will be checking its route table or ARP table, ARP table, and it identifies that, okay, it's trying to go to 10.0.0.0.3, which I don't have. So it will try to send, check its ARP table, right? Switch 2 gets it. Switch 2 will check, also broadcast that message. Okay. And 3 will respond back and then push to the router. So you can simplify this process. You don't need to send a link, a request to our router because they are in the same network. What you can do, you can make a link between these two floors. So that way, your east-west, your floors traffic directly go between the switches. It does not have to go to all the way to the router and then comes back again. So you can bypass this by having a link between your switches. Okay, so that way, the floor, the PC1 will send the broadcast. The switch will broadcast that to this port and also this port, and switch 2 gets it, and switch 2 will send to the PC3, and the response will be coming back this way. That way, your internal traffic does not have to go to your gateway traffic and looks for and comes back to this switch. So you can put a link here. Okay, so that is how we can make it. But what happens if what will happen if your router go down? Your connection to the entire internet is gone, right? Because you are single threaded. The floor 1 and floor 2, all of the access will be gone. Right? So that is not a good idea. We don't want that to be happening. And what happens if the switch 1 go down? The floor 1 is entirely down. And what happens to switch 2 go down? The floor 2 is entirely gone. So these are all single threaded, meaning like they have only one connection to go out to the internet. If that is gone, they don't have any redundancy. There is no backup link or backup path for this topologies, right? So that's why this is not a scalable design, or this is not a reliable design. For that reason, we wanted to go to a more scalable design. We will look into that now. Okay, so that is called core distribution access layer design, which will be used in enterprise networks or bigger network designs. Okay, any questions until this point? Okay, this is a carbon copy of this one, what we are discussing, but we'll look into it. That is internet. This is core router 1, core router 1. This is core router 2. This is distribution switch 1. This is distribution switch 2. Access switch 1. Access switch 2. And access switch 3. Access switch 4. From our earlier diagram, so this will be floor 1, and this will be floor 2. Okay. Floor 1, floor 2. So now let's say we have PC, PC2. So PC1 have 2 connections. Okay. So now tell me, is this looks like a fully redundant network or no? Does it look like if one device go down, we have a different path or no? Tell me that.
Yes.
Right? For example, from the PC1, it will go to the switch 1, and switch 1 will send that packet to the distribution switch 1, and distribution switch 1 will be sending that to the core router 1, and the core router 1 will be sending to the internet. This is one path, right? Or the switch 1, it can send to switch 1. Switch 1 can send to the distribution switch 2, and it can send to the core router 1, and you can go to the internet. That is path, that is different path. And there is also different paths. So switch 1 to the DS1, DS1 to DS2, and go to the core router 1. Or switch 2 to DS2 and to DS1, or then to the core 1, and then go to the internet, right? So there are multiple paths. There are multiple ways to go to the internet here, right? So not only one path. I think we can make like a combination of more than like 6 paths or 7 paths here, right? Between the devices, they can go all the way to the core router 1, or they can go to all the way to the core router 2. Even if one router go down, for example, if say core router go down, that's fine, right? The switch 1 will go to the DS1 or 2, and from there it can go to the core router 2 and then go to the internet. This looks good on the paper, but there are a lot of drawbacks on this as well, because the switch 1 has to choose whether to use DS1 or DS2. And DS1 has to choose whether it has to go to router 1 or router 2. right? And sometimes it can also cause a loop. For example, switch 1 will send the packet to the DS1, DS1 sending the packet to the DS2, and then DS1 sending it back to AS1 and causing a loop between here. Right, so there are different drawbacks for a full mesh topology. There are different protocols to avoid that. The spanning tree protocol will be used to avoid the layer 2 loop, and also to select one path over the other. There are different protocols like HSRP, VRRP to select one device over the other. So we will discuss them in detail more when we talk about those protocols itself. But if you look at the current design, it is the most commonly used in campus, like hospital networks. A small, like for example, if you take Macy's store, which has 2 floors of Macy's, and they want to intercommunicate, you will be seeing some sort of small network like this. Or if you are looking like an 3 or 4 building hospital, if they want to intercommunicate between them, they will use this sort of design. Okay, so they will connect floor ones. I mean, they will connect building one into one access switches. They will send it to the distribution switch at the end of the building, and they'll be connected to the core, and they will able to communicate between them. This is how you will see from small 2-floor building to multiple buildings. They'll increase this, right? They will add one more here, right? So this is one more building. This can be in a one more building. This can be in one more building, and they can be intercommunicating with the routers. So this is scalable. Any questions till this point?
No.
Anyone? Any questions, guys?
No, sir.
Okay. If there are no questions, we'll move on. Well, before we move on, let me. Okay, in the same diagram, where can I put the firewall? Tell me that.
Distribution to the core.
Okay, answer 1 is distribution. Okay. Next answer. I have 17 people or 15 people in the class, and I heard only one answer. I need more answers, please.
Yes, sir. Distribution to the core.
Okay, so you're saying if I put a distribution to the core firewall, it will work, right? Okay, let's put a firewall there. Let's see how it works. So there are 4 links between the distribution to the core. Which link that you want to put 4 firewalls? Or let's do this. Okay, let's do this. So let's say this is
Two
a
firewalls to the 2 switches, maybe.
so you want to put, let's say, a firewall and a firewall, 2 firewalls, okay? And put here. Okay. So you guys are saying this will be firewall. This will also be a firewall. This is distro switch 1, distribution switch 2. This is core router 1. Two. Okay, core router 2, you get the idea. And then you have the internet here. Okay. Okay, so there is a attacker here coming from the internet. So you are saying that putting a firewall here is the best option. When you have an attacker here in the internet, do you think putting a firewall here is the best option?
Sir, what if we put a firewall in between core and internet, core layer and internet?
Well, that's an answer too, right?
Internet.
So tell me, guys. So now the firewall got shifted here.
Mhm.
Okay. So now there is no firewall here. It is just as plain as this design. But we put a firewall here and we put a firewall here. And the attacker is coming from the internet. Okay, we can block him here or we can block him here. And what if the attacker is here? Inside the company. I know it is very rare. We don't see attackers inside the company because we legitimately hire the employees. We know who we can trust. It is very rare. But what if the attacker is here? How are we going to protect it? How are we protecting our whole network?
Again, a firewall between access layer and distribution also. We might need more firewalls.
But it's not feasible, right? How many firewalls you gonna put? Every firewall costs, if it costs like $20,000, I cannot keep on purchasing firewalls everywhere.
So we can monitor the access of this user, no, sir?
I cannot monitor every user all the time. A user may be turning out a rogue at some point, right? But what is the feasible condition here, guys? What is the easiest way that I can control the users, right? So I can do two things. One is putting the edge firewall, that is for sure. That is the most common firewall that I should be putting. And I don't need the firewall between the core and distribution switch. That is not needed at all. Okay. Because we are the one who are managing the core router and core router 2, DS1 and DS2. These devices can trust each other. And if the users want to communicate between the floors, right, we can control them at the access layer itself. We don't need to put a firewall here. Instead, we can turn on the host firewalls on each machine. What is a host firewall? Inside the laptop only, we can turn on the host firewall where we can protect what the user is doing. I mean, we can control what the user is doing. We can turn on the host firewall. We can do that. If we don't have access to the host firewall, we can turn on the port security on the access switch port level. We can allow, block, deny the traffic on the access switch level itself. So we can turn it like ACL here to block the ports. We can turn on the port security, like we can put like a MAC address security. MAC address. We can do MAC address filtering at the access port itself, saying that I wanted to allow only this MAC address. I wanted to block this MAC address. That is called MAC security. We can do that. We can do installing a firewall on the laptop itself, like that's an option 1. For example, I can turn on, for example, like Semantic. It's an endpoint protected software. You can turn it on the laptop itself. That way you can allow, deny, block on the machine itself. So that is called micro-segmentation, right? So we are segmenting using a software on the machine itself by denying or allowing the traffic on the laptop itself. We can do that. But we as an engineers, if you wanted to control on the switch port, we can do that with a MAC address security or ACLs. We can block them there. Is this clear?
Yes.
Yes, sir.
Yes,
So
sir.
who will be able to control that host firewall?
So if your company is small, let's say you have only 10 laptops. If you are a security engineer, it's your responsibility to log into each laptop, install that software, and present it to them before you hire an employee, right? But if you have like 1,000 people, there is a solution called MDM, Mobile Device Manager, which will push the software to all the devices in a single go. So there are softwares just like MDMs, which can install all the softwares to all of your devices. But if you have only small network and you can manually log into each device and then you can install it. But that is not part of a network engineer, that's job of a security engineer. Okay, network security engineer or security operations engineer or network infrastructure engineer. There are different roles for it. But when you're in the market, you may be going to different jobs. You might get a job to install Semantic on all of your laptops, right? You might be going to a security engineer job. We cannot guess that today. But understand that to protect the endpoint security, we need to have a solution like micro-segmentation. What is micro-segmentation, guys? Micro-segmentation means trusting no one, denying everything. On top of that, we will be allowing the traffic. For example, let's say there is a host. I will block all the communications of the host, but allow what I need to go out. For example, there is a brand new laptop, guys. Let's say there is a brand new laptop. On this laptop, I will block everything. Like I cannot go to Google, I cannot go to Facebook, I cannot go to Cisco.com, I'll block everything. with the host firewall, but I will whitelist them one by one, whichever I want. Like I want to allow google.com, okay, allow it. So that is called whitelisting. We block everything. We trust no one. We manually decide what to allow and what not to allow. Okay, so that is called whitelisting. But what is blacklisting? We allow everything, but we will deny only few sites. For example, we will deny Facebook, we will deny gambling.com. We will allow everything, but we will put the blacklisting on some of the sites. Tell me which one is more secure?
Whitelisting.
Yeah, whitelisting is more secure because we are blocking everything. Initially, we'll block everything. We allow what we need really. So we can do that. But as a network engineer, if you don't know the concepts of semantic, if you don't know the concepts of microsegmentation or whitelisting, blacklisting, if you are a pure network engineer, you can put the blocks on the using an ACL with the IP addresses. As a network engineer, you don't have control to the user machines. You can have only control to the switches and your routers. Sometimes you get firewall access as well, but you will get only read-only access. But if you are a security engineer, it's your responsibility to control your firewalls, but you cannot control your routers and switches. But I want you guys to be a network security engineer, not as network or security. I want you to be both. I want you to learn firewalls and also the networking. Okay. What's the time? Okay. So this design is for campuses and enterprise networks. Now let's. Okay, 757. Okay. So there is another design, guys, which is called spine and leaf architecture. This design is used till 2015, 2017 timeframe. Even now they are using this design for the campus networks, but there are data centers, guys. Let's clear all of this. There is a big data center, right? So now what they did is very similar design. right? So this is called spine. These are called spines. These are called leaves. These are called border leaves. And this is the internet. I mean, obviously there will be a firewall. Okay. So this design is a little different because they did not have layer 2 only here, right? They wanted to have the layer 3 here. And they had layer 3 between these links. And they had layer 3 between these 3 links, or layer 2. They can be layer 2 or layer 3, and they go to the internet. So doing this way, you will have the gateway, the router capability at the leaf layer level. By doing that, they can use the traffic. For example, there's a PC here. The switch will be connected. Well, this is the PC. The PC will be connected to the switch 1 or switch 2, or they can use both the links because these are layer 3. They can load balance between both of them because it's a layer 3, because the gateway sits here. And from here, they can use any of these 8 links, any of these 4 links to each spine. They can hash, for example, they can send one packet to this one, they can send one packet to this one, and they can send one packet to this one, and they can send one packet to this one. And from here, they can use any of these links to go out. So we are not blocking one link or the other. We are using full use of all the links at a time. So there are many protocols involved here. For example, VXLAN. For example, you need to know the concept of eVPN services. You need to know concept of underlay, overlay. So there is a lot of technology involved to understand this topic. This is out of CCNA syllabus, but think that when someone says a spine leaf architecture, think that they are talking about a new design in the data center. The spines are acting as your distribution. Think about these are your distributions, and leaves are like your access layer, and border leaves are like your core layer. But the whole idea is, instead of doing the layer 2 like switches, they will use the layer 3 functionality at the access layer itself. Okay, we will discuss, if we do the CCNA data center, then we will discuss about these topics in detail then. But for now, just think about the spine leaf architecture is the data center version of the core distribution and access layers, and your layer 3 sits at the access layer itself. It does not have to go all the way for the gateway to go to the core. The core sits, the layer 2 sits here itself. Why it has to sit here? It can use any link with redundancy. It can use multiple links at the same time. It does not choose one path or the other. It has multiple paths. It can have multiple ways. For example, let's say there is a location A and location B, and there are 2 ways. Okay, and you have 2 cars. Okay, instead of your both cars going in one path, you can use one car to go this way and the other car to go this way. That will reduce some time because you have multiple paths. The same applies here. You can have multiple paths in this design because the layer 3 routing protocols like OSPF, EIGRP can load share between your links. I don't want to confuse you guys by talking more about this topic, but for your ideology, I'm just talking about the spine and leaf architecture. It is not part of the CCNA syllabus at all. Okay. we'll stop there and we'll leave the floor for questions for 5 more minutes. I'll stop the recording.